Folks, today is not a challenging lesson, but you will get confused unless you really kind of focus in on what we're doing, okay? So today we're going to talk about, yesterday we talked about linear approximation. Today we're going to talk about differentials. And they're used in somewhat the same capacity. So we have a function, and then we have a line L that refers to the linearization of that function. Everybody okay with that? Okay, so then what we're going to do is we're going to look at how the function changes over time. So as I move to the right, okay, and then I move up, you can see that this is the change in the function, correct? Whereas the blue represents the change in L, correct? So as I move further to the right, what's going to happen to those blue and green segments? They're going farther apart. What's going to happen as I make that distance smaller? So the fact is that the blue is an excellent representation for the green in small windows, correct? So we call this green portion the change in y. It's the actual change of the function. Delta y. We call the blue dy. That refers to the change in its rate, so the derivative piece here, okay? L, the linearization. Now the nice thing is that this part below, delta x is the same as dx. dx is the same as delta x. So our movement to the right is the same for both, but the movement up is different. You see that? So why would the differential of a function be useful? Okay, we say that dy is the differential. Dy approximates what? Delta y. Dy approximates delta y for small windows or intervals, however you want to think of it. I'm not going to get too technical here. So, wouldn't it be a nice thing to come up with a formula for dy? Well, we've always said that dy over dx is basically the same thing as f prime, right? It mean the derivative. Well, let's just multiply both sides by dx. You get dy is equal to f prime of x dx. Easy peasy. So we can find out the change in dy, or we can find out dy rather quickly. Let's go to an example. Just find the differential dy and then evaluate it for given values of x and dx. So dy, again, is equal to f prime of x dx. So dy is equal to, I need to come up with a derivative for f. What's the derivative of the function? So it's negative x to the negative 1. Yes. The derivative of negative 1 over x is 1 over x squared. Katea. Nice throw away. Times dx. What's that? Yes, this is my differential. We are now going to approximate delta y by finding dy. So in other words, we can find this dy value very quickly. All we have to do is plug in our knowns. What is x? 2. So 3 Whoop. 3 plus 1 over 4 times what is dx, or 1 half. So the dy is equal to, that would be 12 fourths, so 13 fourths times 1 half is 13 eighths. So that means if I go over half of a unit, I go up 13 eighths, approximately. Okay? This function will go up approximately 13 eighths of a unit. Okay, we are almost there. All right, let's do it. Shh. We want to find dy. dy is equal to f prime of x dx. Look at 3 over x plus 1. My good friend Spence said, hey, let's use the product rule. He's right, or the quotient rule. He's right. We can use the quotient rule, or we can use the chain rule. Chain rule is going to be a lot easier in this situation. 3 times x plus 1 to the negative 1 power. What's the derivative of the inside? 1. What's the derivative of the outside? Negative 3u to the negative 2, right? So we got dy is equal to negative 3 over x plus 1 squared. That's that derivative, okay? Times dx. So I want to find dy. So dy is equal to, what do I do? Yep, so I got negative 3 fourths times 1 over 100, negative 3 over 400. So that tells me if I have a change in x of 100th, then the change in y is approximately negative 3 over 400. Okay? Now we're going to see this played out in an example where we're actually going to draw some of the segments in place. You really want to pay attention here so you understand what's going on in your assignment. It's not difficult, but it is new. Okay? So we're going to draw x cubed plus 1. What is the x value that we're using? We're using 1. So this is the question that the problem is trying to ask. It says compute delta y and dy for the given values of x and dx equal delta x. Sketch the diagram, show line segments with dx, dy, and delta y. The question is asking if I have a change in x of 0.2, so I'm going to go over 0.2. So that's my delta x, which is dx. Those are the same. So if I move 0.2 to the right, the question is, how much do I go up? This is your first question you got to try to answer. Does that blue segment represent dy or delta y? Delta y, because it's the change of the actual function. Dy is the approximation when you're using the line. So suppose it would be challenging for us to actually compute what that delta y was. And instead of computing delta y, we wanted to compute dy. That would be that segment. So which is going to be bigger, dy or delta y? Delta y is bigger. So dy is going to be an underestimation. An underestimation. Okay? So some people had questions about overestimations and underestimations. So it says actually compute. So I've got my segments drawn there. I have my dy, my dx, my delta x. I have all that drawn. But it says actually calculate delta y and dy. We'll do dy first. We know that dy is equal to f prime of x dx. What is f prime of x? 3x squared dx. What value do I plug in for x? 1 times 3 is 3 times what is dx? 0.2, and I get 0.6. So which segment up here does 0.6 represent? The green, the red, or the blue? It represents the red. So when I compute the blue segment, is it going to be bigger than 0.6 or smaller than 0.6? And it's very easy for us to calculate our delta y value. Delta y is just going to be the function evaluated at those two spots. So we're going to type in f of 1, but if we went over 0.2, that'll bring us to 1.2. So we're just finding out what, how close our estimation is right now. So in order to do delta y, we take f of b minus f of a. So we're going to type those in and see what we get. Typing in 1 is pretty easy. When you type in 1, what do you get? 1 to the third is 1, plus 1 is 2. It's okay. 1.2 to the third. Then we add 1 to it, and I get 2.728. And so we get 0.728. So does that make sense with our drawing? Yeah, because this is just slightly larger, correct? So you can decide if you think that 0.6 is a good estimation or not. Obviously, the further you travel for x, the worse your estimation is going to be. Let's try another one similar to that, okay? Square root of x minus 2. What does the graph of the square root of x minus 2 look like? Very good. The Callan whoop. What's the spot at which I'm evaluating? At 6. Okay, and what is my change in x? What am I going to travel to the right? I'm going to travel 0.1, and I know that this is not to scale, but it would be very difficult to draw this to scale, okay? So go over 0.1, and what does that represent? Delta y, delta x, dy, dx. Yep, this is dx, which is the same thing as delta x. Those are the same. And then I'll use this blue segment. Is that delta y or dy? Delta y, because it's the actual function. Let's suppose that the delta y value is very difficult to compute. Then instead of calculating delta y, we would calculate dy. So you can see in these small windows, it's tough to draw it so that you can see it real well. But that's kind of, with the use of different colors, that's kind of a helpful way to show it. Okay, so we want to compute dy. dy is equal to f prime of x dx. How do I compute f prime of x? Chain rule, yep, find the derivative. U to the 1/2, 1 over 2 roots of u, x minus 2 and 1. So therefore dy is equal to 1 over 2 roots of x minus 2 dx. That is my differential. What do I plug in for x? 6 minus 2 is 4. Square root of 4 is 2. 4, so I got 1/4 times 1/10, and I get 1 over 40, which on our calculator would be 0.025 if we were to actually write that as a decimal. Okay. Well, let's compare that to delta y. Let's actually subtract our function values. Very good. 6.1 and 6. Well, plugging in 6 is going to be kind of obvious. 6 minus 2 is 4, square root is 2, so minus 2. So I'll have to do the 6.1. Square root of 6.1, and then I'll subtract 2 from that, and I get, what happened? Oh, 6.1 minus 2, excuse me. So square root of 6.1 minus 2, and then minus 2. And I get 0.0248. Well, that seems pretty close to 0.025, doesn't it? It's all relative, though. It's all relative. This is a very abstract representation. You can see that the 0.0428, that's obviously smaller. The delta y is smaller than the dy. But let's apply these to 3 different situations that you could actually use, and then we'll end after this. It says use differentials or equivalent linear approximation to estimate the given numbers. We want to do the square root of 64.3. First thing we're going to do is identify a function. Are we okay there? Now, do you know the value of square root of 64.3? What's the number close to 64.3 that you know the square root of? So we will choose x to be 64. Okay? Now, we're not trying to evaluate the square root at 64. We got to move a little bit, don't we? How much do we move in order to get to our 64.3? So that means dx is equal to 0.3. So I have my f of x, I have my x value, I have my dx. So let's figure out the change in y, because I know that the square root of 64 is 8. But how much up from 8 should I go to approximate it? Should I go up 0.1, 0.2? What should I go up? So let's figure it out. dy is equal to f prime of x. What's f prime of x? 1 over 2 roots of x times dx. What do I plug in for x? I plug in 64. And I get 8 times 2 is 16. So 1 over 16 times 3 over 10, or 3 over 160. 0.3. So tell me this. What the heck does 3 over 160 mean? Because it sure as heck is not the square root of 64.3. Go up from what? Not 64, but from 8. Right. So the square root of 64 is 8. So I go up from 8 3 1/60ths, and that's a good approximation. Or at least they say it is. Let's see if it is or isn't. The square root is 64.3. I get 8.0187. If I do 8 plus 3 divided by 160, pretty close, huh? So again, using approximations, helpful piece. 3.01 to the 4th power. Very good. F of x is x to the 4th. What is my x value? 3. What is dx? 0.01. So we're going to approximate 3.01 to the 4th power. So dy is equal to f prime, or x cubed, dx. What do I plug in for x? 3 cubed, 27 times 4, 108 times 1 over 100, or 108 over 100. which is like, what, 54 over 50? Like 27 over 25. Well, I know that 3.01 to the fourth is not 27 over 25. How far it goes up from 81? So 3 to the fourth is 81, right? So from 81, we're going to go up 27 25ths, and we'll get to 82 and 2 25ths. If we try that, 82 plus 2 divided by 25, I get 8208. If you take 3.01 and raise it to the fourth power, you get 82085. So that's a good approximation. Last problem. Oh, that's kind of what he does. What's Calc 2. Anyway. All right, so we've got a circle, and it says that, whoop, I don't need to draw that. I'm used to related rates of change. We have a circle, and it's measured, and we find that the radius is 5.4. Now, you measure a circle, and you realize, well, how accurate is that 5.4? And they say that it's a possible error of 0.1 centimeters. So what's the smallest that the radius of the circle could be? 5.3. What's the biggest at the 5.5? It's somewhere in between there. Now, will that impact our area? I wonder by how much it will impact our area. Well, we can use differentials to figure out. It's no big deal. What's the formula for area? Derivative of area, a prime. Derivative of pi r squared, 2 pi r prime. This is just saying that if the radius changes a certain amount, like how much could the radius possibly change? 0.1. Then how much would the area change? That's what this is saying. The radius changes a certain amount. What would the area change? Let's figure it out. What's the current radius? 5.4. What's the possible change? So 2 pi times 5.4 times 0.1. And I get 3.39. 3.39 what? Centimeters squared. So the area could actually change by 3.39 centimeters squared if we were to change the radius by 0.1. Is that a lot? It's hard to really know, right? Like, what if the original area was like 3 and it was going to change by 3.39? That would seem like a lot, right? What if the original area was 1 million and it changes by 3.39? So we got to figure out what we call relative error. And that's the last part of the question is, what's the relative error? And the way we figure out relative error is just take the error divided by the known total. So we have 3.39 that could be the error. How do we calculate the known total area? Yeah, pi times 5.4 squared. So 3.39 divided by parentheses pi times 5.4 squared. 0.037. Or 3.7% relative error. So, you know, you can decide if 3.7% is too much or that's okay. Your assignment is listed at the on your homework cover sheet. It's a book assignment. It's posted online. That's it. Which day is your test?